This is a combination of parts 5 through 9 of my series, Programming in Assembly. We'll learn about conditional branches, use this to create a program that determines if a user inputs an uppercase or lowercase character, and then finally develop another program that uses the stack to reverse a string. Now, let's see how we can make dynamic programs using conditional jumping. By the end of this, we will have a program that differentiates between lowercase and uppercase characters, but first, let me explain the compare command. The compare command takes two values and sets different flags in the CPU. These flags can be used by conditional jump commands to skip or repeat pieces of code depending on the compare command's results. Here are six of these conditional jump commands. Each one uses the previous compare command's results no matter how many instructions are between. JE jumps to the label if the two values compared are equal. JNE jumps if the values are not equal. JL jumps if the first value is less than the second. JLE jumps if the first value is less than or equal to the second. JG jumps if the first value is greater than the second. And JG jumps if the first value is greater than or equal to the second. Now let's take a look at this program and break down each section. In the data section, we define the character we want to compare and three strings that we will use to show the program's results. Next, like always, we tell the program to start at the start label. Then we print the first message, as this will be displayed no matter the value of the character. We compare the value of the character to uppercase Z. Uppercase letters have a smaller value in ASCII than lowercase, so we know the character is uppercase if it is less than or equal to uppercase Z. Note that we are assuming that the character is a letter in the alphabet. Also note that we must specify the size of the value in memory. In this case, it is a byte because characters are represented by bytes. If the character is less than or equal to uppercase Z, we jump to the label named uppercase and move the address of the uppercase string into the register RSI. If the character was not less than or equal to uppercase Z, the program continues to the next line. I like to put a label there to match the format with the other label. Because the label is not needed, I create a comment that looks like the label. Comments are text in the code that are ignored by the computer. To create one, type a semicolon and then your comment, followed by a new line. Next, we move the address of the lowercase string into RSI and jump to the label named done. We jump because otherwise the program would continue to the next line and move the address of the uppercase string into RSI. Finally, we set up the registers for the write syscall, and fortunately for us, uppercase and lowercase are both 9 characters long. Finally, we exit the program with an exit code of 0. Let's modify our previous code to say goodbye to the user at the end. First, we'll add the goodbye string to the data section and use the write syscall to print it to the console. But as you can see, there's a problem. Our code no longer fits on the screen. It's also annoying to have to retype the same code each time we want to write to the console. We can solve both of these problems with macros. A macro is created by writing %sign macro, the name of the macro, and some text, ending it with %sign end macro. Everywhere the name of the macro is written will be replaced by the text defined in the macro. When defining a macro, you also must write the number of arguments that will be passed in. You will choose where these arguments are located in the resulting text. When you use a macro, it essentially copies and pastes whatever you defined it as with the arguments given. Let's move the first section of our code that writes to the console. Instead of hard coding in the location and length of the string, we will use a macro that takes two arguments. The first argument as the location of the string and the second argument as the length. To use the arguments, we write a %sign and the index of the argument starting at 1. Next, let's replace our goodbye code with the macro and write the first message at the beginning with the macro as well. This helped a lot, but the code is still pretty long. Let's create a new file named io.asm, io meaning input-output, and move the macro into this file. Back in the main file, at the top, we will include io.asm, allowing us to use what's written in it. Last time, we cleaned up our code by creating the write macro in our IO file, which is great, but now we have an IO file that can handle the O, which stands for output, but cannot handle the I, which stands for input. To fix this, we will be creating a macro called read, but before we do this, let's look at the layout of the BSS section. The BSS section is similar to the data section, but you don't declare a value when creating the labels. Instead, the labels point to areas of memory that are automatically set to 0. To reserve room in the BSS section, you write a label followed by a colon, the size of the data to be stored, and the length. The size can be a byte, word, dword, or keyword. The length declares how many of those to reserve. Here's a simple example that reserves 1 byte, giving it the label char. Then, we set up the registers for the read syscall. The syscall number for read is 0, so RAX will hold 0. RDI holds the file descriptor for the file that you are reading from, but for the console, we will set it to 1. RSI holds the location where the characters will be stored, and RDX holds the number of characters to read, which will be 1 because we just want to read 1 character. Let's now create a macro called read, which will take in 2 arguments, the address to store the characters and the number of characters to read. We'll update the macro to set RSI to argument 1 and RDX to argument 2. Now, returning to our original program, let's make it to where the program asks for a character and then checks to see if it is lowercase or uppercase. First, let's remove char from the data section and add it to the BSS section, because the value is unknown until the program runs. We'll also add a string to the data section that prompts the user to input a character. At the beginning of start, we will first use the write macro to prompt the user. Then, using the read macro, we will store the first character that the user enters into the address in memory pointed to by the label char. The rest of our program will run the same as before. Let's look at how you can use the stack and in the process create a program that reverses a string. There are two commands that we will use: push, which adds a value to the end of the stack, and pop, which removes the value at the end of the stack and stores it in a destination. Let's first visualize how the program will work. We will loop through each character, pushing them one by one onto the stack. Note that the stack is grouped by 8 bytes, so whenever a character is pushed onto the stack, there are 7 bytes of wasted space. Next, we pop each character off of the stack, storing the values in the original string. Because we will start from the left when iterating through the string each time, the order is reversed. Let's make the program that reverses a string. We'll start with our program setup and add a string to the data section. A very common way to denote the end of a string is by adding a null character at the end, which is just the value 0. Our program will use the null character to know when it is done iterating through the string. We'll first move the address of the first character in the string into RDI. We'll create a loop by adding a label to the beginning and a jump command at the end that jumps to the label. Also, at the end of the loop, we'll use the increment command to add 1 to RDI, which means it's now pointing to the next character in the string. Then, we'll add some code at the beginning of the loop that will conditionally break from the loop. Registers are 8 bytes large, but we just want to get the byte stored at the address that RDI holds. This means we just want to move the character into the lower byte of RAX. Let's quickly take a look at the different subsections of a register. In this example, I'll show the RAX register, but it applies to all registers. As we've seen, the entire 8 bytes are called RAX. The bottom 4 bytes are called EAX. The bottom 2 bytes are called AX. AX is split into two sections, the higher byte AH and the lower byte AL. So in our program, we will move the character into the lower byte of RAX by writing AL. We then compare the character that AL holds to the null character, and if the values are equal, we jump out of the loop. If the character is valid, we push the character onto the stack. Because the stack can only add or remove 8 bytes at a time, we push using RAX, not AL. After the first loop, we set the second loop up the same way. Because we only need to read the character once, we won't move it into AL. When we compare the character to the null character, we must write byte in front of it. Before, when we move the value into AL, the assembler could assume the number of bytes to transfer because we specify the size of the register. Now we must explicitly state the size so it knows how many bytes at the address to compare to the null character. We compare the character to the null character to check if the end of the string has been reached. If it has, we jump out of the loop. Otherwise, we pop a character off of the stack and replace the current character in the string with that value. We'll end the program by printing the reverse string using our write macro and then exit the program.